Alrighty, so this will be our final exam review for Physics 220. Firstly, our particular exam is going to be on Monday, November 17th at 10 o'clock in the same room as our normal class. What can you expect? Well, it's going to be formatted just like the regular tests. So you've seen what the tests look like already. The formula sheet will be with it. The only difference, there are two big differences. First, the final exams are 2 hours. So that means there can be twice as many questions on this test. So likely you can expect something like between 12 and 15 questions. 12 to 15 questions. The other big difference is this is cumulative. So that means it's on all of the topics, not just the latest topics. Okay. Now, that's the formality. Again, formula sheet will be provided, same formula sheet as you've been using on all the previous tests. So nothing new there. Best ways to study. Of course, this is one of the first exams you're going to have, probably. And I know you have other exams you have to study for as well, so in my opinion, to save as much time as possible, the most efficient way is study your two tests. We've had 2 tests so far, so study them, redo them, just get a blank sheet of paper out, redo the test without looking at your answers or anything like that, and see if you can do them. If you could do all the test questions perfectly fine and get them all right, then you're probably going to get 100 on the final exam. The reason is because we have a whole bunch of different topics, a whole bunch of different questions that I could ask. However, when I give something like a homework set, I can't give you an infinite number of questions, so I pick and choose those that I find most important to put on the homework. And then again, for the exams, same kind of a thing. Now I have even more limited number of questions I can ask. So of those important questions, I'm choosing the 5, 6, 7 questions out of them that I find to be most important, or at least get to the foundations of the topics we've been talking about. So if that's what I thought for the exams, I still think that's true for the final exams. So first, start with that. If you need more practice from there, then I would look at the homeworks and worksheets that were provided in class, because again, I made those questions, so they're the same types of questions I would ask on an exam and the like. So first do the test, then look at the homeworks and the worksheets, and if you still have a whole bunch of time on your hands and you just want to practice some more, that's when I would look at the practice problems and solutions that were posted to Canvas, just to get more practice in. But this one right here, studying your test, redoing your test with a blank sheet of paper, that's the most efficient and best way to prepare for the final exams, because your final exam will look very similar to those. All right, so with that, what are the topics? Well, we kind of have 3 big overarching topics we've gone over this semester. Of course, we started with a math review and vectors and things like this. I'm not going to test on that because every other question I give you about physics already tests your math and your vector stuff. So there's no reason to just give a purely math question on a physics test. Where we really started the physics was in the topic of kinematics. So kinematics, we had 2 forms. We had 1-dimensional and 2-dimensional. The equations, of course, the equations will be on the formula sheet, but just to remind you of them, we had x equals v naught t plus 1/2 at squared. We had vf squared is v naught squared plus 2ax. And then acceleration is the change in velocity over time. course, if I do it in calculus-y formatting, dv dt, or the second derivative of the position with respect to time. Right? They all mean the same thing. So those are our three big equations, and these three equations work whether we're doing one-dimensional or two-dimensional. Of course, one-dimensional just means everything's moving in the same direction. So it's a x direction, or to the north, or whatever, north or south. So those are easier because you don't have to worry about the complications of the mathematics of vectors. You know, what if I have two different directions going on? Something's moving towards the east, and then it changes direction to the north. The math that goes along with that is just a little bit more complicated, whereas with one-dimensional, you get rid of that complication and you just focus on the equations themselves. Questions that were like this are things, you know, you have a plane. Here's my plane. It's flying with some initial velocity for a certain amount of time, and then maybe it accelerates for another amount of time, and the question could be how far did the plane travel, and what's its final velocity due to the acceleration. So again, everything's moving in the same direction. Or a bird's flying with a certain speed, then the wind blows against him, slowing him down. Now how fast is he moving, and what's the total distance he traveled? Those types of questions. Two-dimensional is the same type of concept. The only difference is now we're introducing multiple directions happening. So these were the questions like you have a cliff, you have a rock, and maybe you throw the rock horizontally, and it's going to fall down, and you want to know how far will it go by the time it hits the ground. Or you have a cannonball shot at an angle, some theta, with some initial velocity, and you want to know what's the maximum height. What is the time of flight? What's the final velocity when it hits the ground? What's the range? The projectile motion style questions. So all of these are kinematics. If you have multiple directions, you just now have to worry about breaking all your information up into x and y components. And whenever you use one of these three equations at the top, you do everything in the x direction or you do everything in the y direction. Remember, you cannot combine different directions in one equation. So that was the kinematics stuff. From there, we moved on to Newton's laws. So now we have physics problems with the use of forces instead of just, you know, what's the motion? What are the dynamics of the situation? Now we're going to apply forces to objects, and we want to know how do those forces make the objects move. So obviously the big equation here is the sum of all the forces is mass times acceleration. That's Newton's second law, or the form of Newton's second law we're going to use for these types of questions. What are the basic questions here? You have a block resting on a frictionless surface. The block has some mass m, and you're going to apply some set of forces, F1, F2, F3. And you want to know, number one, what's the acceleration of the block due to all of these forces? And number two, what's the normal force acting on the block? So again, the normal force, normal mathematically means perpendicular. So the normal force is the sum of all of the forces that are acting on the block, which are perpendicular to the surface. So normal force does not contribute to the acceleration. It's only the parallel forces that give you the acceleration. You know, how much of the forces are parallel to the surface? Those are the ones that are going to slide you along the surface. Perpendicular forces, they don't contribute to your acceleration, except indirectly. And that's where we get things like friction. If friction is in the problem, then remember I have to give you mu, the coefficient of friction. Maybe it's 0.1 or 0.2 or whatever it happens to be. And with friction, that tells us mu times the normal force will give you the frictional force. So the more normal force acting on the object, the more friction that object's going to feel. Of course, if it's heavy, heavy, heavy object, then when it tries to slide over carpet or grass, then it's really digging in to the roughness of that material, and so it feels more friction. Whereas if it's a very light object, it just barely glides along the surface, so it doesn't really feel the roughness as much. That's one way of trying to interpret, your frictional force equation. So that's why normal force is important. If we don't have friction, then normal force really doesn't do anything. We don't care. Now, we still calculate it just for the practice, but only the parallel forces tell you acceleration. When you have friction, normal force contributes to friction, and friction is a parallel force. That's why it is important. So that's the first type of question. We also had inclined planes. So this is a ramp with the block sitting on the ramp. Ramp is inclined at an angle theta, and maybe there are forces acting on this block as well. Same type of question as before, only now instead of being on a nice horizontal surface or a nice vertical surface, we're on an angled surface. So here you do the exact same process, but instead of finding x and y components, now you're finding parallel and perpendicular components. Same thing, you just call it a different name. What else went with Newton's laws? Well, we also had things like elevators. So a person's in an elevator standing on a weight scale. As the elevator moves in certain ways, what will the weight scale say about the weight of the person? Are they heavier? Are they lighter? Things like this. We had pulleys. So here, we can have 2 blocks attached by a rope over a pulley, some M1, some M2, and we want to know what's the tension in the rope and what's the acceleration of the blocks. How do they move? Those were the pulley style problems. And then we had what I would call third law style problems, which were the ones like you have multiple blocks connected by ropes, and that system is being pulled with a force. You want to know what's the tension in each one of these ropes here, tension 1 and tension 2. Or you had 2 blocks touching each other, block A and block B, and you push on the system, and you want to know what is the reaction force from B back to A. As you push the system, you push on A, the A pushes on B, and now A and B are moving to the right. But because A is pushing on B, Newton's third law says B must push back on A with the same force, but in the opposite direction. Equal and opposite reaction. So these two types of problems are very, very similar, although they seem different. One, you're looking for tensions between boxes. The other one is what are reaction forces. But in essence, you solve them the same way. Look at the system as a whole. Calculate the acceleration of the system. Then peer into the first object and say how much force is required for him to get that acceleration. Some amount of force. Then you say he was given a total amount of force. He only needs this much. Whatever's left over is what he gives to the next guy. Whether he gives it as a tension in rope 1 or he literally just pushes on block B. Once you know that, that means block B pushes back on A with that force. Okay? So these were the Newton's laws style of problems. Final topic we went over was work and energy. So with this, first big one was work itself, which is force times distance. But here we learned about one of the new versions of multiplication because we're dealing with vectors now, this one being called the dot product. The dot product basically interprets how much of one vector is in the direction of the other. And what that means for physics is when you want to calculate the work done on an object, if you're applying forces to that object and the object's moving, then the only amount of force that contributes to doing any work for you is the amount of force which is in the same direction as the motion. In other words, if I have a block and the block is sliding to the right now, and I push straight down, well, that's not helping the block move to the right or to the left. It's not speeding it up or slowing it down. It's doing nothing. It's perpendicular. Who cares? However, if I push against the block in the x direction, let's say, then now that force that I'm pushing does contribute to the work. In fact, this is negative work because I'm slowing the object down. I'm going against its motion. And if I push with some angled force, then I would look at how much of that force is in the correct direction. That is, what's the component of the force in the direction of motion. If I want to know the total work done on an object, because it's got multiple forces happening, all you got to do is add up all the forces which are in the right direction. Some are positive, some are negative if they're going with the motion or against the motion. Add them all up, multiply by the distance, and that gives you the total work. Or the other way of doing it is you just find the work done by each force individually. Then for each one of those, add all of those works up, and that's the total work done. However you want to think about it, it means the same thing. From there we said, okay, now that we know how to calculate work, what can we do with it? How is it helpful to us? And the way it's helpful is with the work energy theorem. Once you know how much work is done on an object, what we know about the work is that it'll change the kinetic energy of the object. So that means, if you know the work, that tells you 1/2 mv final squared minus 1/2 mv initial squared. We're usually going to take the initial velocity to be 0. It wasn't moving until you started applying the forces. And so by knowing how much work is done, you can calculate what will be its speed once it reaches its final position. You know, if it moves 5 meters, how fast is it moving at the 5-meter mark? That's why the work is useful, because it allows us to calculate something we actually care about, which in this case is the velocity. Also, we did conservation of energy, which is probably one of the most important topics in physics, energy conservation. And the way we looked at it was to say the kinetic plus the potential energy initially for a system. So you have a system, maybe it's a block at the top of a hill, or it's a pendulum where you've moved the pendulum bob over by a certain angle, whatever it happens to be. That system has some energy. It's got some energy because of its motion, which is kinetic, and it's got some energy because of its position. That's the potential. Now remember, the potential energy, there's multiple different types. There's gravitational, spring potential energy, electric potential energy, all sorts of different types. You add all of those up, those are all called potential energy. So if you add up the kinetic plus the potential, that's the total energy of the system. And the big universal law says that whatever that number is, the total energy, it's conserved. So as long as you don't have outside influences working on the system is closed, then that total amount of energy will always be the same, no matter where you go and check. So if I have something like a hill with a block at the top of the hill, and the block's going to slide down, well, no matter where along the path this block is sliding, if I investigate its total energy, it's always going to have the same amount. If it started with 1,000 joules, it has 1,000 joules everywhere along the path. What will change is that 1,000 joules maybe started with all 1,000 was potential and none of it was kinetic. And then maybe later on, some of that 1,000 of potential has been transferred over into kinetic energy. So maybe it's 800 is in potential and 200 in kinetic. It's still a total of 1,000, but now where that 1,000's coming from is being transformed around into different types of energy. So that means if we know the kinetic and potential initially, then That must be the kinetic plus potential finally. And then remember, my advice, or if you're getting used to doing energy conservation problems, the way I would handle them is I would ask myself 3 questions given some system. So for instance, maybe the system is a spring, there's a block on the spring, and you compress the spring by a certain amount, and then you're going to let go, and the block's going to rise up this very tall hill, and you want to know how high will the block go. Well, in order to do this, of course, conservation is our equation, and we need to stick in the different types of energies, the different numbers, and everything into our equation. So how do I know what's important and what's not? Do I have potential energy or not? Ask myself the same 3 questions every single time. Once I know what the states of the system are, so the initial state and the final state, then I can ask the questions. So here, the initial state is, I've got a block of mass m, compressing a spring whose spring constant is k, all of this is given in the problem, by a certain amount, and I'm waiting to let go so that the block can start to move. Okay, that's the initial state. So in that state, now I ask the 3 questions. First question, am I moving? If I am moving, then I put 1/2 mv squared down. If I'm not moving, then it's just 0. Next question, part of the potential energy, am I some distance above the ground? If I am, then I have mgh. If I'm not some distance above the ground, then that's 0. And the last question, am I messing with a spring right now? If so, 1/2 kx squared. If not, that's 0. And I just add these up, and that's my initial state, kinetic plus potential. Again, we have 2 forms of potential. And now I move over to the final side. What's the final state? Well, for this particular example, I've now let go. The spring has shot my block, and the block has moved up the hill as far as it'll go. Now, in that state, I ask the same 3 questions. First question, am I moving? If so, 1/2 mv squared. If not, that's 0. Next question, am I some distance above the ground? If so, mgh. If not, that's 0. And then last, am I still messing with the spring? If so, 1/2 kx squared. If not, that's 0. Once I've asked those questions and stuck all the equations in, now I just start plugging the numbers. What's the mass of the block? What's the initial velocity? What's the initial height? All those types of things. How much did I compress the spring? And you'll be left with a single unknown in your equation, and you just solve for that unknown. That's the best way to do these energy conservation style problems, in my opinion. Of course, once you get comfortable that it just comes automatic, you don't literally have to ask yourself the questions, you just kind of know. But that's the best way so you don't forget anything. Now, how is this modified? Of course, this energy conservation equation only holds, if you remember I stated it, under the assumption that the system is closed. There's no outside influences. If you do have an outside influence, then the energy can be taken away. Or you can add energy to the system that's not accounted for in this equation. So how do we handle a situation where the system allows the energy to be taken away or given back, or however we do it? The way we do it is through the use of work. The reason is because in math, and thus in physics, if you have an equation, then all the things in your equation, each term in your equation has to have the same units. In this case, this is an equation of energy. Each term here has energy units, so anything we stick into this equation must also have energy units. And the only other thing we know right now that has the same units as energy is work. So we might have a system where the block is going to slide down the hill, but now it's a grassy hill, so it's got some friction to it. How do we account for the fact that friction is going to slow our block down, whereas if there was no friction, it wouldn't have that effect? And the way we do it is just by incorporating work, and the way I do it is kinetic plus potential plus work initially is kinetic plus potential plus work finally. Where kinetic plus potential, those are the same as before. That hasn't changed. The only difference is these two terms here. So this work is the work you would plug in when the work is being done to speed you up. So you are on a skateboard and you kick the ground to speed up on the skateboard. Or you are Wile E. Coyote and you attached a rocket to your back to speed up to try to catch the Roadrunner. Those types of things speed you up, and thus the work done would go on this side of the equation. Whereas the work on this side of the equation slows you down. So these are things like friction or air resistance. Things where there's an outside influence on the system that's soaking energy away from you, soaking it up. So you're going to move slower than you would have had it not been there. Now, if you forget which one speeds you up and which one slows you down, I probably should have put the green and red the opposite way here. The way you remember it, or the way I remember it, is I just ask myself, okay, let's say the system has friction. So the work is a frictional work. It's going to slow me down. Which side of the equation should I put that number on? It's 300 joules of work. Well, let's say I were to put it on this side of the equation over here, the left side. What would be the effect of that? Well, pretend there is no work. You'd solve for your kinetic energy, you'd solve for your velocity, and you'd get some number. Now, had you put the work on the left side, when you go solve for that velocity, you're going to get a number plus that extra amount of work, in essence. Not exactly, but in essence. So that means whatever your velocity would have been, you're now adding to it. You're now getting faster. So that would imply that work that's on the left side of the equation speeds you up. Whereas if I put the work on this side of the equation, the right side, again, I solve for the velocity, I get some number. But if I have the work on the right, now when I go solve for the velocity, I move that work to the left side. And when that happens, it becomes negative. That means it's subtracting away from the velocity. So the velocity goes down, you get slower. That's how I remember which side is slow down and speed up. So given a system, you can have something like, here's your spring, really complicated system. And you want to know what is the velocity down here at the bottom of the hill if there is a rocket attached to this block and there's some work done by friction. So the work done by the rocket is maybe 500 joules. Work done by friction is 300 joules. You're compressing the spring, you let go, it's going to slide down. So kind of a little bit of everything. How would you handle this? Well, pretend there's no work first and do your conservation of energy equation. K plus P initial is K plus P final, leaving space for the work. Then look at each individual piece of work here. So the friction one, that's friction, that slows me down. So I'm going to put plus 300 on the right side of the equation. And then the other one, the work done by the rocket, that's speeding me up. So I'm going to plus 500 on the left side of the equation. And if I have other works, maybe work done by air resistance is 200 joules. Then I just add another 200 to the right. I just keep adding more and more of these numbers. I never put any of these things in negatively. They're always just adding to the equation. So all the works that are going to slow me down, I add them all up, I put it on the right. All the works that are going to speed me up, add them all up, put them on the left. And now I go about solving my equation just like I would have before. No difference. All right, so those are all the topics. We have work and energy. So work is force times distance. Work is equal to change in kinetic energy. That's the work energy theorem. And then conservation of energy with and without work. We had Newton's laws. F equals ma, that's the big guy, as well as frictional force is mu times the normal force. And then we could have a whole bunch of different versions of this. You could have it on a flat horizontal table. You could have it on a vertical wall. You could put it on a ramp, an inclined plane. You can have elevator problems. You can have pulley problems. All these types of things are all incorporated into basically just F equals ma. That's all it is. Remember, with pulleys, you have multiple pieces in your system. You've got 2 blocks. Each block gets its own F equals ma. And you're going to wind up with 2 equations, 2 unknowns, the tension in the rope and the acceleration of the block. So you need 2 equations to solve for 2 unknowns. Equation 1 is for mass 1. Equation 2 is for mass 2. And then the first topic, kinematics. 1-dimensional and 2-dimensional versions. So again, you can have a rock being thrown straight up with an initial velocity. It's going to come back down. You want to know what's the time of flight. How long will it take to hit the ground? That's a 1-dimensional problem. 2-dimensional problem, you're on the cliff, you throw the rock, but now you throw it horizontally, or you throw it at an angle. Now you have both horizontal and vertical motions to worry about, but you're using the same 3 equations. It's still these equations here. The difference now is we deal with the vector issue. X and Y components separate. Anything that goes into equation is either all X stuff or all Y stuff. If you could figure out your sines and cosines, this shouldn't be a big deal at all. Okay, so those are all the topics for the final exam. Again, 2-hour test, probably somewhere around 15 questions if I had to guess. Formula sheet will be attached to the final exam as always. Study your 2 previous exams. If you could do those on a blank sheet of paper, perfectly fine. You'll be perfectly fine on the final exam as well. If you have any questions, of course, feel free to email me. I'll be happy to help. Just, take a picture of the problem you're trying to solve and where you're going wrong or whatever, and I'll be happy to look at it and email you back what I think. And other than that, I will see you for the final.